All right, a whole nother application. So let me get started. You just imagine that I need to exert a force of 100 pounds to get my car moving. And I want to move my car 10 feet. In this second case scenario, I need to apply a 100-pound force to get my car moving, but I want to move it 100 feet. So question, in which scenario, the first or the second, is the force exerted to get the car moving greater? And the answer is neither. It's the same amount of force. But I want to be able to distinguish between these two problem situations because I think I'm going to be out of breath much more here than up here. And so I'm just going to make up a definition out of thin air in such a way that numerically I can distinguish between these two scenarios. So here's my definition. If I multiply force by the distance for which the force is being applied, numerically these two scenarios will be distinguishable, and I'll just give it a name. I'll refer to the product of force and distance as work. Now, putting this to practice, suppose I have a tank whose front facade is in the shape of the graph of that equation, and the top portion of the facade is an inverted isosceles trapezoid. Now, this tank is filled with water, and there is indeed a spout rising 1 meter above the top of the tank. Question, how much work is required to pump all the water out of the tank? Now, I'm not even going to begin to grade your work unless I first see axes being labeled. I need to see the axes in the picture and them labeled in the picture as well. Because the graph of this equation, at least from negative pi halves to positive pi halves, has this local min point 1 meter above the x-axis, I'll place the x-axis 1 meter below that special point. At least with the x and y axis placed as such, I don't have to describe any kind of translation with that equation. All right, next. I want to now identify an arbitrary slab of water. Can you imagine? From here to here, subdividing the interval into n subintervals, concentrating on the ice subinterval. And over that ice subinterval, I want to consider this rectangular slab of water. The reason why it is horizontal is because as long as the vertical height of that rectangular slab is very, very small, the distance any point in that slab moving up to the top of the spout is going to be about the same. Of course, when we take the limit of the Riemann sum, there is no change in y values. So let me show you how I'm going to do this. I am going to first compute the volume of that ice slab of water. I will next consider the amount of force required to get the ice slab of water moving. And use my man-made definition of work, I'll talk about the work involved in getting that ice slab moved up to the top of that spout so it can ooze out the side of that spout. So here I go. Volume. Well, what you see in red is just a rectangular solid. Its volume is length times width times height. So its length, well, actually, let me stop for a minute. Do you mind if I label a point? That point right there, I'll label as this. This length is x of I asterisk, so that length is 2 times it. This length is given, it's fixed. And the vertical length is merely a small change in the y direction. Now, I'm in a bit of trouble with that factor. You know what's going to happen in the end. I'll take the limit of a Riemann sum, and that delta y will become a dy, meaning my variable integration will be y. So I need to change that in terms of x sub I asterisk. Sorry. I need to change that in terms of y sub I asterisk. But that's the relationship. So here's another name for it. Next, as I suggested, force. But force is just mass times acceleration. We typically use the letter G for acceleration. Mass can be interpreted as density times volume. Now, G is approximately 9.8 meters per second squared. The density of water is 1,000 kilograms per cubic meter, and the volume is described as such. Next on my list, the work required to get that ice slab of water moving up and oozing out that spout is the product of the force needing to get it moving with the distance I need to move that ice slab of water. Well, force is already given. I'll multiply by the distance that ice slab needs to move. To get that d sub I, look at my pretty picture. This is 1 meter, so that's a half a meter. If that's 1/2, then this y value is this. 2 units above it is this. 1 more unit above it is this. Secant to 1/2, 2 plus it, 3 plus it. So this y value is already labeled. Here's a distance that ice slab needs to move so that it oozes out that spout. But this distance is nothing more than this large y value minus a small y value. So d sub I is this. Now, if I take the limit of the Riemann sum, the total work involved is merely going to be an integral with this coefficient, and here's the rest. As far as my bounds are concerned, for the portion with this as a boundary equation, that's from this extreme y value to this one. And I'm only half finished. Because now, if this ice slab of water is in this inverted trapezoidal portion of the front facade, then I think how I rewrite x sub I asterisk is going to be different. Let's talk about the equation at line. Well, that's 9th grade high school algebra. So force will not change. There's my G, there's my rho. This does change. And the work involved in getting that ice slab moving up and out that spout is a product of these two. Now, I'm getting a little nervous. I do seem to have a problem with board space. So now that we have this relationship, let me get rid of this. That's just copied. And now I'm going to multiply to that, my distance. This will be right here. Now, it's not going to change from before. If you picture this ice slab of water up here, this y value is still y sub I asterisk. So the distance I need to travel is nothing more than, yet again, that large y value minus a small one. It doesn't change. What does change is how y sub I is interpreted. Now, when I take the limit of the Riemann sum, I'm going to get another whole integral that I will add to the first integral. Here is a coefficient up front. All this is in the integrand's position. But these ice slabs of water are ranging from this extreme y value here to just this extreme y value up here. So if you don't mind, I'm not going to finish. After all, you and I don't even have a technique yet to anti-differentiate that factor in the first integrand. So this question is merely a setup. I'm hoping this is sophisticated enough for you to get started on the work. No pun intended.